My name is Sarah Black. I'm a researcher in the Rachnovsky Group at the University of California, Irvine. Today I'm going to tell you a little bit about my research. Most of us have heard the term protein. You may know of it as an important part of your diet. But what exactly is a protein? What do they do? Why are they so important? Imagine your body as a factory, and its job is to keep you alive. You have assembly lines to carry out all of your important functions, like breathing, healing, and digestion. These assembly lines rely on groups of tiny machines working together to reach their final goal. Each tiny machine is known as a protein. Proteins are these amazing devices that can do one thing really, really well, over and over again. Sometimes, though, machines break down. Their parts don't work together as they should. And with proteins, this can have dire consequences. Misshapen proteins lead to a variety of terrible diseases, like Alzheimer's and Parkinson's. In order to fix these proteins, we need to understand how they work. And what's the best way to figure out how a machine works? Take it apart. See what's inside. See how all of its different parts work together. Unfortunately, the machines in our body are so tiny that we can't see them with our eyes. Bacteria, known as E. coli, have over 3,000 proteins within just one single-celled organism. A grain of rice is more than 10 million times the size of hemoglobin, an important protein in your blood. So if we can't use our hands to take these proteins apart, how do we figure out what they look like? Moreover, a protein's function is highly dependent upon its structure. If we know what a protein looks like, we can learn about its activities. Imagine a screwdriver. Each different kind of screwdriver has a differently shaped head. The head of the screwdriver determines what kind of screws it can interact with. You might be able to use a flathead screwdriver to turn a Phillips head screw, but it probably won't work as efficiently as you want. Sometimes it may not even work at all. A protein's efficiency level can be the difference between breathing and suffocating. This is true for people who suffer from sickle cell anemia, all due to changes in the shape of the protein hemoglobin. Usually, scientists take pictures of proteins to learn about what they look like. They expose these images with X-rays or electrons. Unfortunately, though, these photo shoots can be very difficult to set up and often result in blurry snapshots. More detailed pictures of proteins will provide us with more useful information about protein structure. My lab's job is to teach us more about protein structure. But first, I have to tell you a little bit more about what we know about protein shape already. Proteins are made up of a bunch of tiny building blocks known as amino acids. There are 20 different kinds of amino acids, and each can be represented with a different letter of the alphabet. Here, we have a pool of all 20 amino acids that your body can use to make a protein. When making a protein, your body chooses the amino acids from this pool and strings them together in a chain. After all the amino acids are chosen and connected, the chain is folded up to become its final protein. We don't have a good idea of the rules required to fold a protein, which makes learning about their shape very difficult. This is where I come in. I design small chemicals, much smaller than the proteins themselves. My chemicals are used as tools by biologists. We call these tools chemical crosslinkers. On the molecular level, they look like this, but you can imagine them in this simpler form. Think of these crosslinkers as microscopic tape measures, and think of me as a tailor. I take these crosslinkers and I use them to measure different parts of a protein, and then I take all of that information to learn what a protein looks like overall. More specifically, you can follow my workflow here. First, I take a protein of choice and I expose it to a whole bunch of crosslinkers. The crosslinkers attach to the different amino acids in the protein through chemical reactions. After that, you have one large cross-linked complex of protein and crosslinker. We then chop up this complex and search for our cross-linked pieces. After that, we feed the information to a computer, and that gives us a picture as the output. In our lab, we have mostly studied crosslinkers that interact with building blocks labeled K. We hope, though, that someday there will be enough tools that any protein you want can be studied. My dream is to make a chemical toolbox filled with all sorts of tape measures so that anyone can study any protein they desire. Currently, I'm looking at crosslinkers that interact with building blocks labeled C and labeled Y. Once we have a clear picture of both broken and working proteins, we can design better medicines to fix them. When we have detailed information about protein structure and shape, we'll know exactly how they need to be changed. Just think of me as your own protein repairman or woman.